Okay, nice. Hi, good morning, everyone. So it's week 11. This week, I'm going to talk about greedy algorithms. All right, so let's just begin. Okay, so start the recording. A little bit of administrative matters. This week's lecture, this Thursday, should be on the topic of reductions in computational complexity. And in my opinion, it's one of the most difficult topics for CS3230. So I highly recommend to watch attempt to watch it live, perhaps like in case you have any questions, you can clarify, you can seek clarification like immediately during lecture, even if you haven't caught up. So even if in the past few lectures, like on amortization, dynamic programming, and greedy algorithms, even if you haven't watched them, I think it's fine because the topic is pretty independent of those chapters, except maybe the lecture will be using some examples based on one of those lectures, like maybe I don't know, the knapsack problem I think might be mentioned again in the lecture. But I think I'll try my best to see the slides in advance, and if in case like those of you who want to attend the lecture live, I'll try to fill you in the things that you need to catch up, like the least amount of things you need to learn in order to catch up for that. Okay, so yeah, again, just try your best to attend the lecture, and if you can't attend the lecture, try to watch it early, because I think the topic might be confusing, okay, based on my past experiences teaching this and as a student last time. Okay, so let's go on to today's table of contents. We'll just talk about greedy algorithms today. We'll go through two greedy algorithm questions. Okay, so the first three questions are related to the same problem, and the fourth one is a different problem, but uses the greedy algorithm nevertheless. Okay, so greedy algorithms, again, it's quite related to dynamic programming, which we talked about last week. So dynamic programming last week, we say that, oh, we try to brute force, but carefully. Okay, and then we try all the sub problems. You remember the triangle we had last week? We tried a lot of triangles before like making a conclusion, right? So this was dynamic programming last week. So today we'll be talking about greedy algorithms, right? Where we do the kind of the same thing. We try to do a bit more brute force, but even more carefully. And I think the key difference compared to dynamic programming is in dynamic programming, you try all the sub problems, right? Try a lot of sub problems. But in greedy algorithms, the optimization is that you just pick one sub problem. So you just pick one that this double quote, the best one. Okay, the best one, typically you take the maximum of something or the minimum of something. You just pick one sub problem. Okay, and this reduces the time complexity a lot, because usually the total time to compute all the sub problems, right? Like last week, it might take O(n) time, right? There are n sub problems to compute at this level. Okay, but for greedy algorithms, typically it only takes O(1) time, because you just compute one sub problem and that's it. Although there might be some pre-processing, which we'll see in a bit. Okay, so let's go on. Okay, so when to use DPA in greedy, same thing as before, you need optimal substructure. And to recap, optimal substructure means that the optimal solutions can be reconstructed from smaller sub-problems, right? So the optimal solution to the smaller version, right? Maybe you can merge it in some way, or you don't need to merge it at all. So optimal solutions to smaller problem can be used as the optimal solution to the bigger problem. Okay, so the thing that you have to recall is that in greedy algorithms, you just try one sub problem which you choose greedily typically. Okay, and that's it. Okay, not exactly that's it yet. So the thing is, right, about dynamic programming last week, I mentioned that, oh, we have to ensure that we cover the cases as much as possible, right? But in greedy algorithms, I say that, okay, you just need to try one. So what about the cases that you didn't try, those sub problems that you didn't try? So now what you need to do is you have to prove that indeed this greedy choice will still give you the best optimal solution. Okay, so even though you made the greedy choice and you ignore a lot of sub potential answers, you prove that this particular answer that you choose is gonna still end up the best one. Okay, so this is what allows greedy algorithms to work. Okay, so typically we prove this by the cut and paste argument. Okay, so at a high level, we'll see this in a bit later on with the example, is to try to cut out the current optimal solution. So start out with some optimal solution. Just assume some optimal solution exists, right? What you do, you cut out like a part of the optimal solution, and then you paste something using the greedy choice. Okay, we'll see that in a bit. But again, you try imagine taking out, you have an optimal answer, take out part of it, and then put something that was made by the greedy choice, and then show that this solution, it stays either as good or it doesn't become worse. Okay, so we'll see this later. Okay, don't worry. So this is just really giving you a high level idea. All right, so the first question is this pairing files, right? We'll talk about the optimal substructure of it. So so there's this person, Bob, right? Bob has music files that he wants to burn into CDs. So I think you guys are not like super young, so you should know like CDs, as in like, you know, like you guys should, I think people my age still know what CDs are, and I guess you guys should be around my age as well. We know what CDs are, I hope. I hope there's none of you there who don't know what a CD is. Okay, so we want to burn into CDs. So the CD storage capacity is 100 megabytes. Okay, not fantastic by today's standards, but CD is 100 megabytes, let's say. Okay, so I think is there's this funny constraint where there's no 2 music files per CD. Okay, so wait, no 2 music files per CD. Okay, wait, yeah. So okay, so then given set A of file sizes, each smaller than 100 megabytes. Okay, let this notation min CD A denote the minimum number of CDs required to fit the files described in A. Okay, meaning you have some file sizes, right? You have some file sizes. Sorry, you have many files. Maybe you have like 10 music files, and each of them are smaller than 100 megabytes. Okay, then you want to store this music files into the CDs. Okay, and then, well, because each smaller than 100 megabytes, so you can hope that you can store 2 music files per CD, right? There's this constraint that a CD requires has a limit of 2 music files. Okay, so maybe let me, do I have a picture later? Okay, let me just draw it out now. So let's say I have a CD, right? Okay, wait. To be consistent, later on, the diagram I have will have a rectangular CD. Okay, so so this is a music file, and this is another music file. So maybe this is like 50, and maybe let's make this 44 and make this like 50, 53. This is legal. Okay, this is legal. So you can store two music files in a CD. But what's illegal is that even if this was like, this is another music file that's like maybe 1 megabyte, this is not allowed, because now you have 3 music files per CD. This is not allowed. Okay, but the question is, right, so we can do this kind of pairing. We can put 2 music files in the same CD, right? So that suggests to us like, hey, maybe like if I have 10 files, can I fit it into 5, for example? Can I fit it into 5? But of course, that's not always possible, because maybe all of them are like 90 megabytes. Let's see, 90, 90, 90, 90. Then maybe the minimum is 10 CDs. Okay, so this is the min CDA notation. Okay, so this is the question, right? So so we would like to describe the optimal substructure, right? So we want to describe like some equation to show that by taking the optimal solution to the smaller sub problem, we can get the optimal solution to the current problem. Okay, so the question, sorry, so no 2 files per CD means no more than oh yes, I think I meant no more than 2 files per CD. Yep, sorry. So no more than 2. Yep, my bad. Yeah. Okay, so yeah, I think that's what I meant. So files can be split across CDs. Okay, wait, I might have been confused by my own transferring to the slide here. No 2 music files per CD. No 2 music files per CD. So my description here says that cannot split music file, no burning to. So there are, I think it's both. So in a CD, right? So in a CD, you can have 2 music files, like 2 different music files. Okay, so like a 30 megabyte music. So let's call this music A, and then maybe like 70 megabyte music B. Okay, so this is fine. Okay, but what's not fine is that this 30, right? You cannot split it into 2, and then maybe like store it in another CD. So this like 15 A part 1. Then maybe another CD you store like the 15 A part 2. So this is not allowed. So this is not allowed. Let me try and remember the phrasing again, because okay, yeah, it's both. Yeah, so I think I might have transferred from the slides wrongly last time. I'm not too sure, or not accurately. But again, the constraint is that you can store two different music files in a CD, right? That's fine. But for a single music file, you cannot split it in across CDs. Okay, so sorry for the confusion, but I hope that clarifies. Any other questions about the question? Okay, so all right, so the equation to describe the optimal substructure, right, is one of these things, right? So it's a bit subtly different. All of them have pretty much the same equation, but the only difference is like what you take out of F1 and what F1 and F2 are. So this notation is trying to say that, okay, you have a set of CDA, and then you subtract away F1 and F2. So you can think of it like a set A without F1 and F2, right? It's taking out and recurse on that problem. Okay, so which of these describe the optimal substructure? Okay, meaning it's trying to say that, okay, so CDs in the smaller, okay, optimal solution to the sub problem, okay, you can use it to construct the optimal solution to the current bigger problem. Okay, so slightly different, just have a read. So I'll give you some time to think about it. Maybe not 3 minutes, let's say 2 minutes, let's say 11:15-ish, right? Like 11:15-ish. It's phrased maybe slightly confusingly, but we'll see in a bit, okay, what this kind of means. So I'll just give you this time to like answer and at the same time understand the question, because we'll go through this like question 1, 2, and 3. We'll use this context. Okay. Let's read. Yes, so there's a question in the chat. The backslash means without. Yeah, you can think of it as without. Yeah, set subtraction. Yep. Okay. Okay, great. So I think I'll just go on. It's fine if you don't fully know what this is talking about, but I hope you minimally understand the question. So most of you got it right. Okay, so a couple of mistakes, but that's okay. So first of all, I'll just say the option 1 does not work, right? So the thing is, like, we cannot simply pair any two files and still be optimal. So here's a simple counter example. Okay, so let's say the set A, right? The set of music files has sizes 10, 20, 80, and 90. Okay. Optimal solution to this is 2. You can pair up like 10 and 90 together. Okay, you can pair up 10 and 90 together and 20 and 80 together and fit in the same CD. So we get 2 CDs. All right. But if you choose any pair, right? The question says if you choose any pair of files, means that it's legal for me to choose 10 and 20 together. Right? So if I choose 10 and 20 together, put it in the same CD, right? So this put in the same CD. Okay, so the minimum CD of this set is not equals to 1 plus the minimum CD of 8090, right? 8090 is the set without 10 and 20. Right? I take away 10 and 20 and then recurse on it. Because the minimum CD of putting 80 and 90 together is 2. 80 and 90 are alone, right? So they cannot fit, you cannot pair them up together. Okay, so they cannot pair up together, and so that's why clearly this approach does not work. Okay, so I think this slide should be pretty intuitive enough. It just means that you cannot anyhow choose a pair, But if you need me to go through the counterexample again, do let me know over PM or whatsoever. Okay, so yep, so as I said earlier, optimal solution is 2, but then if I choose any pairs, then I might end up with like answer of 3. All right, so okay, so this is just a break slide because the next slide is gonna look similar, but it's different. So option 3, this time we have another counter example for option 3. Option 3 says you choose the largest and the smallest in A, and then recurse, right? So this suggests like, oh, maybe there's some greedy choice, right? You always choose the largest and smallest. Reasonable. I think that's a reasonable train of thought. Okay, but the thing is, right, the largest and smallest may not even fit in a single CD, right? So like for example, 10, 20, 30, 95, 99. If you choose, this is the optimal. You have 4 CDs in order to, excuse me. So you only need 4 CDs to pair up things as needed. Like that's the optimal answer. But the choose and largest and smallest, like 10 and 99, right? They don't even fit. Like they don't even fit into a single CD. Okay, they don't even fit into a single CD, and so the recursion doesn't quite like make sense. Okay, so this is me just trying to work out the numbers, but again, I hope it's intuitive that it doesn't make sense for you to even choose the largest and smallest because they don't even fit into a single CD. So the math gets all messed up. I just put the math in the slides in case you're interested, but like intuitively, I hope it's clear that smallest and largest paired together, they might not even fit. Okay, so all right, so let me go on to the option that's correct. So most of you chose this option, right? And let's show that this is fine. Okay, so at the high level, what we'll say is that we consider any optimal solution, right? We don't know what the optimal solution is, how it looks like, right? So we choose any optimal solution, then we remove any pair that is in the same CD in the optimal solution, and we say that the rest must be stored optimally. And if it's not stored optimally, we can always reduce the total number of CDs used by using optimal solution. Let's see a picture in a bit. Okay, so maybe I'll just go through the option again. Like it says, for any pair of files F1 and F2 that belong on a single CD in an optimal solution, right? So this kind of is a bit like the ordering is a bit funny in the sense that we claim that we know what how the CD is stored in an optimal solution, right? Then you remove it, and then it can, by recursing on the set that with that those 2 CDs removed, you can get the optimal solution to the current one. I think what I just described might have been confusing, but let's see an example, like a diagram to show this, right? So imagine these are the CDs, right? Imagine rectangular CDs for some reason. Okay, the circles are the files. Okay, a bit funny, I know. So circles are the files. So assume, right, you can magically choose a pair of files in the optimal solutions. Again, we don't actually know how the optimal solution look like. Let's just assume we know, like we have some magic optimal solution. Okay, then you know how to choose a pair of CDs. Choose a pair of files that belongs to the optimal solution. Okay, we'll actually show how we can do so later. But for now, assume this can be done. Okay, this can be done. You can have a pair of CDs stored in the optimal solution. In you have a pair of files stored in a CD in the optimal solution. Okay, so you have this. Okay, so now after choosing that pair, we have this sub problem, right? So we have this sub problem of 4 files left. Okay, we have this sub problem with 4 files left, and then you want to find the optimal answer to this. We say that, oh, let's say that we can solve this optimally too. We can solve this optimally to construct our optimal solution. Typically, we try to prove by contradiction. So we solve it optimally by supposing not, right? We suppose that we can actually get the optimal solution to everything without going through the optimal solution to the sub problem. Okay. By the way, today I'll say this a lot, like optimal, suboptimal, sub problem, big problem. So let me know if it gets confusing. Okay. So let's say, right, because of our assumption by contradiction, we can find an optimal solution, right, by using suboptimal solution to the sub problem. Okay, the claim here is that it takes 3 CDs. This is the suboptimal answer. The answer that is not optimal uses 3 CDs. Okay, uses 3 CDs, And by using this suboptimal answer, this answer that is not optimal, you can construct an optimal solution. Because we are proving by contradiction, we assume that it is possible to do so, to get the optimal answer by only using something that is not optimal. Okay? So, because we say that, oh, okay, that's always possible. Now what happens? Let's replace the non-optimal answer with the optimal answer. Okay? The optimal solution to the sub-problem is actually just 2 CDs, right? Earlier, I say that the not so optimal answer is 3 CDs. But the optimal answer actually requires it can require 2 CDs. Okay. I just want to mention, you don't need to have the concrete values. You can just say the optimal solution is like less than equals to the suboptimal answer, right? Because the optimal answer has to be even better. Okay, so it's the less than equals to. You can argue it abstractly with inequalities, but here I just want to show a concrete example to make it like stick. Okay, so I have 3 for the suboptimal, and I have 2 CDs for the optimal solution. Okay, but if I call it the optimal solution, then the initial thing that I claim, right, was optimal was actually not optimal at all. We contradicted ourselves, because earlier on I claimed that with 3 CDs in the suboptimal solution, I can get the optimal solution to the everything, to the original problem, and that is 4 CDs. That's 4 CDs because 1, and then 3 from here. Okay, so our claim was that was the optimal answer. 4 was the optimal answer. That was our initial claim. Okay, but by assuming not, right, proving by contradiction, we got an even better result simply by using the optimal solution. Simply by using the optimal solution to the sub-problem, we get an even better answer of 3. So something like a contradiction. Okay, we started off with 4, but by replacing the smaller one with by replacing the solution to the sub-problem with the optimal one, we bring it down to 3. Okay, so I would like to stop for questions, okay, because I understand some might be confused, like with all this contradiction and whatsoever. Okay, but any questions about this, or is this okay? If it's okay, like please give me a thumbs up. All right, a couple of thumbs ups. I think the underlying idea, if you closely think about it, should not be that difficult. It's very intuitive, right? Like if you want the best answer for the current problem at hand, you always keep wanting the best answer. But this is just trying to prove it a bit more like rigorously why it works. Okay, so thanks for the thumbs up. And in case you are still confused, do let me know over chat. Okay, and I'll go on. Okay, so as I said earlier, just now I showed a concrete example, right? Like the optimal solution has 2 for the optimal solution to the sub problem. But you don't actually need to do this. Again, you can just use like inequalities to argue and so on. Okay, I gave concrete number for illustration only. All right, so what did we just show, right? So we might have forgotten of our original goal. So what we just showed is that this problem exhibits optimal substructure, and meaning that you can reconstruct an optimal solution to the current problem by using optimal solutions to the sub-problem. That is just what we showed. And now what we should do is that we find out how to choose a pair of files correctly. Because just now, what we did was just by magic, we assume we can, right? By magic, we assume we can choose a pair of files that fit in the optimal solution. Now we'll show how to exactly, the next question will show you how exactly do you choose this pair of files. Okay, then after we choose the pair of files correctly, we recurse to find the optimal solution to the sub-problem. Okay, so this is the plan for the next question. So how do we make the greedy choice? All right, so there are a couple of options here. So assume any optimal solution contains pairs burned into a CD. Okay, so assume it's all stored in pairs. Select all that is true, right? So there are a few statements here. The first one says smallest file must be included in a pair in some optimal solution. Okay, so the pair F1, F2, where F1 is smallest file, F2 is the largest file, such that F1 and F2 fit into one CD must be included in a pair in some optimal solution. The third one, the pair F1, F2, where F1 is the smallest file and F2 is the largest file, must be included in a pair in some optimal solution. Okay, so that was just me reading all the options, but it's okay if you don't fill in archipelago, but I want you to like give it a bit more thought about it, right? It's nice if you fill in archipelago, but let's give you like a minute or two to read the options, at least understand the question. Okay, and if you don't understand, again, do ask. Okay, so I think I'll just go on. Okay, all right. So the answer is actually options 1 and 2. I think a lot of you chose option 2, and this is because maybe you translated directly from the first problem. But actually, option 1 is also true. Okay, the smallest file, right, can be included in a pair in some optimal solution. Okay, so we'll show why. We'll show why. Okay, so but I think option 3 is great. No one chose option 3. Option 3 is false clearly because smallest and largest file might not even fit. So I think it's not worth discussing for too long. Okay, but option 1, right? Why is it the case that smallest file must be included in a pair in some optimal solution? So I want to mention here there are many possible optimal solutions, many possible pairings, right? But what we are saying here is that the smallest file, there must be one of it among the many possible answers, right? One of it must have the smallest file be included in a pair. At a high level, the argument is like this. So if it's not included in a pair, right? If imagine it was alone, right? You swap it with any file included in a pair in an optimal solution. The number of CDs do not change, so it stays an optimal solution. At the high level, that's what's gonna happen. Okay, so to put it into pictures, so imagine again rectangular CDs and a lot of files, right? Let's assume right, this kind of like arrangement is optimal. Let's assume this is already optimal. There are two possibilities. Okay, the smallest file over here is either already in a pair or it isn't. Remember, our goal is to show that some optimal solution must have the smallest file be included in a pair. That is our goal. So, well, if we already have an optimal solution, it either means it's already in a pair or it's not. If it's already in a pair, that's trivial. Like you just mentioned it for completeness, okay? Because if it's already in a pair, we call it a day. That's fine, okay? But we don't know if this is possible, right? So again, we try to construct an example. We try to construct an optimal solution starting from like another optimal solution which satisfies our what we want. Okay, so placeholder slide. Let me go on. So now, suppose this is another optimal solution, right? This is another optimal solution where the smallest is not in a pair, right? Let's say like this guy is alone, right? Again, I want mention that there are multiple solutions possible to give you the same optimal result of 4 CDs, right? Here is just another arrangement that really shows that, we have 4 CDs, but in this particular example, this guy is alone. It's not in a pair. So it's always possible for us to construct an example where this is in a pair, because all you have to do is to swap the two. Okay, to take some pair, right? To take some pair and then swap the smallest file into it. Okay, so it will still fit. Why? Because, well, this guy is smallest. The yellow one here alone is the smallest. Clearly, it can fit once if you take this bigger guy out. right? So this guy always fits, no matter where it puts, no matter where you choose to swap it into, okay? Because this is already the smallest. So this is still optimal, right? We started off with 4. We don't change the number of CDs at all. So therefore, we must have that some optimal solution. We don't know which one, but some of it must exist, one of it that contains the smallest that fits in a pair, that's already in a pair. Okay, so that is the argument. Okay, so this is kind of like the cut and paste aspect to it, where you try to cut out from the optimal solution and then paste some greedy choice. And the greedy choice, in a sense here, is the smallest CD. Okay, so option 1 says that there is an optimal solution for the smallest file in a pair if optimal solution contains a pair. Option 2 is really like the full greedy argument. Okay. Before that, like I think I'll just quickly pause if anyone has questions about option 1, because option 2 will use a similar argument. So I think it's worth pausing here. Like, can you give me thumbs up if it's okay? Okay, great. Nice. Okay, so again, PM me if you have problems. But option 2, right, is the greedy choice argument. So the thing is here, right, option 2 says that you take the smallest file, F1. F2 is not the largest file. F2 is the largest file such that it fits. Okay, so this is a subtle difference here. F2, you find the largest one such that it fits to, sorry, F2 is you find the largest file so that it fits together with F1 into one CD. So again, similar argument here. So we assume an optimal solution where the smallest file is currently paired with someone else. It's not paired together with something that fits the best. Okay, so what you do, you swap the two and you argue that it's fine, that it's going to fit. Okay, same as before, we argue the two cases. What if it's originally not paired, and what if it's originally paired? Okay, so let's have a picture about this. Okay, so rectangular CDs again. Let's assume this is optimal. This is the smallest element, right? This is the smallest element. There are two cases. We look at the element that the biggest element that it can fit with. Okay, so among all the other elements, this guy is the one that can fit, is the biggest, and it can fit together with the smallest element. Okay, so there are two possibilities. They are already a pair or they are not. Okay, so case 1, this is already a pair, right? So we are done. We don't really need to argue too much. Okay, so they are already a pair. We are done. So let's view another optimal solution. Okay, let's say something like this. Okay, something like this, where the smallest file is over here on the left. Okay, we have another optimal answer. This is the smallest file, but it's not paired together with the best answer that can fit with it. Okay, if this is the case, what we can do is we just swap these two, right? Swap the current pairing, swap the current pair together with the biggest fit. We argue that this is possible, right? It doesn't violate the 100 MB constraints. Why? Because first of all, by construction, this biggest fit guy, right, can fit with the smallest element. That is by definition of what it means to be the biggest fit. By definition, it can fit with the smallest guy. Okay, so therefore, if you put biggest fit into CDA together with the smallest element, it should fit by definition. Okay, the current pair can fit into B, right? Simply because this is smaller than the biggest fit. Because biggest fit is the biggest that can fit. Okay, that is very weird to say, but like pictorially, I hope it's clear that the current pairing is either equal or less in size compared to the biggest fit. Therefore, it must be able to fit in B as well. So now, again, we didn't create any new CDs, and this is still optimal. Okay, this is still optimal. And so it's possible, right? It's possible to always find an optimal solution where not only the smallest file is in a pair, but the smallest file is also paired together with the largest that can fit with it. Okay, so this is our greedy choice. We know how to make a choice for the current subproblem. And how do we do it? We look for the smallest element and pair it with the largest fitting one. This is our greedy choice, Okay, so the combination of looking at the smallest element and choosing the largest that fits together with it is the greedy choice. So it tells us that using such a pair, right, can give us an optimal solution, and the greedy choice won't hurt our result. Okay, so this is the question 2. Any questions about this? Question 3 is like deriving it and answering. Derive now. Okay, so there's a small nitpick in the chat. Option 1 assumes there must be a pair first, right? So yes, you are right, and actually that is the assumption in the question. So assume any optimal solution contains pair burn into a CD. That was the original assumption, but you are right that we need some pair to exist first. Does this answer your question? Yep, no problem. Yep. Yeah. So if no pair exists in the optimal solution, then this argument doesn't quite hold. Good catch. Okay, so all right. So question 3. So derive an algorithm to compute this. I think it's worth stopping here because this constructing a greedy algorithm is like a common thing you should do. So try and derive this. Fill in archipelago, and we have time for today, I believe. Right. Okay, in archipelago, I just asked what's the minimum number of CDs required. At the same time, maybe you can give like a description of the algorithm as well. Okay, so like give a high level idea, like what should you do if you are given, think of it as you're implementing this in like writing code for this. You're given an array, what should you do at a high level? Okay. Excuse me. Yep. Okay. Okay, let's just give me 1 more minute, maybe. Okay. Yep. Okay. Great. So I think answers are coming in, and most of you have the idea right. Okay. So again, we want to greedily find the first pair, a smallest element with the largest that fits with it. So well, what you can do to efficiently do this is to sort the array. And I think like I'll just mention that in a lot of greedy algorithm problems, sorting is a very common routine, as I've seen it. Sorting is very common for you to in order to do the greedy choice efficiently. Okay, so typically sort the array is the first step that you do, and you maintain 2 pointers where one goes from left to right. Okay, this is to keep taking the smallest element greedily, and going right to left is to keep finding the largest element that can fit. Okay, so then at the end, we collect the remaining elements that were like double quote skipped. So let's go through an example here, right? So again, this is the high level algorithm. Okay, so I've sorted this. and I maintain 2 pointers. So, well, the left 7 can be paired with 91. That's fine. Okay, so they form the first pair. The second one, you advance the left pointer and you see, 12. I can take 12. Who can I pair it with? 12 cannot be paired with 89. So you pair it with 81. It cannot be paired with 89 because the total sum is 101. Okay, so you can pair it together with 81. Advance it, you get 27. 27, pair it, you can only be paired with 62, but not 74, and so on. Okay, I think doesn't get too interesting yet. Okay, here this is where I guess it gets slightly more interesting, where you see that, oh, okay, I stop at 49, the left pointer is at 49, and then the right pointer, I want to pair it with something, but then there's nothing left for me to like pair it together with it. So what I do is that, okay, I guess 49 is alone. Okay, 49 is alone. And then all you do the left is like collect the remaining ones that haven't been paired together, like 74 and 89. Okay, so total is 8 CDs required. Okay, and the time complexity for this is ON log n for sorting, and it only takes ON for pointers traversal. You can think of it as like the left pointer only like advance the entire array once, and the right pointer only traverse the entire array once. Okay, so in total, this takes ON log n time. This whole algorithm of finding the optimal number of CDs only takes ON log n time. Okay, so I'll just quickly mention it again. So first one, sort the array. Second step is maintain 2 pointers from left to right and right to left. The one from left to right is to keep taking the smallest element greedily, and then until you keep finding the best fit. Okay, and once you cannot already, you collect the remaining elements that were skipped. Okay, so that's this question. I'll go on in the interest of time to go to the last question, activity selection, which is a new problem. Okay, in case the algorithm isn't clear, you can ask me later. But this activity selection is given a set of activities. Each activity has an interval. Okay, and these 2 activities are compatible if these time intervals don't overlap. It's just a very like cheap way of saying that, you know, if they're overlapping, they are not compatible. So for example, this timing, right, from 3 to 10 and 5 to 15, schedule clashes like basically. They are not compatible if they clash, and it's fine if they don't clash. And the one end here, right? The one end here is open and closed interval. Sorry. So it's an open interval, and A2 is a, oh, sorry. Okay, I forgot the terminology, apologies, but basically one is inclusive, one is exclusive. So it's fine if it's just nice touching like this. Okay, one is just nice touching like this, that's fine. That means A2 and A3 are compatible. Okay, so the problem here is that in the activity selection problem, we want to find the largest set of mutually compatible activities. So we want to take as many as possible, a largest subset, such that they don't overlap. Okay, find the largest subset such that they don't overlap. So there are several options here. One is you choose the activity that starts last. Okay, so among everything, you choose the starts last. Discard those that conflict with A and then recurse. Okay, so so meaning here, for example, like let's say I have a lot of schedule, right? I have a schedule. So this is the one that starts last. So I take this guy. And then I discard this guy and then recurse on this region. Okay, so this is what it means. The second option is the one that ends last, and the third one is the shortest activity. Okay, the one with the shortest time interval. So no need to fill in archipelago for this, but just notice how all of this is a form of a greedy choice, right? But some of it works, some of it don't. So which one work, which one don't? Give it like a quick thought. Okay, tell what your intuition tells you. Okay. Okay. So give me a minute for this. Okay, so I think a lot of you are conflicted in these options. Like I see a wide range of options for those who actually fill in archipelago. You don't need to fill it up, but I'll go on with the options now. Okay, so okay, so this is okay, optimal substructure wise, what you can argue is that okay, I think okay, let's not talk about this too much about optimal substructure. Maybe I'll talk about after class. But if you want to fit as many lessons possible, which timing would you choose? Like this is an intuition. Let's say you're planning a timetable, right? So maybe you're taking like 8 modules this sem, like 32 MCs. I know some of you are probably doing that much. Okay, but let's say you want to fit as many lessons possible. Which timing would you choose? Okay, so intuitively, or at least I feel that some might think this intuitive, some may not think it's intuitive. What you want to do is to choose the one that starts last. And the intuition is that it frees up the day as much as possible. Let's say you choose this guy that happened to start the last. It frees up all the timing before 6 p.m. Right? So this is the intuition, or at least I hope this can be the intuition of why you want to choose the one that starts last. The answer is actually the one that starts last. Okay, and I'll give counter examples why ends last and is the shortest is not a good example. Okay, but if you choose the one that starts last, intuitively, it should free up all the timings before 6 p.m. and you can potentially choose more lessons, right? Okay, so this is the intuition to keep in mind. So the proof for the greedy choice is like this. Again, assumes this is the interval, right? These are the intervals, and assumes the ones in black are the optimal solutions. Okay, so this is the optimal solution in black in the middle. So if the start last in the optimal solution is the start last in the input, then we are fine, right? If the input, the starting last is the one in the input, then this is the trivial case that I've been showing earlier today. But what if it's not? Okay, so meaning the starting last in the optimal is not the start last in the input. Then what we can do, right? So sorry. Let me say that again. So let's say we have this input. This entire thing is the input, and the middle one is the optimal solution that we have. We say that, oh, we can construct a subset of 3 intervals, right? And this is the max. This is the optimal answer, because with these 3 intervals, we can construct. Sorry, they don't clash. These 3 don't clash, and they are optimal. Okay, so let's say the last in the optimal, which is this guy over here, is not the starting last in the input, which is this one. What we can do is that we can always swap the 2 together. Okay, again, like just now, swap this and this, swap this and this, to obtain that this is another optimal solution that is possible. Okay, so this is another optimal solution that is possible, and therefore what we just showed is that we can choose the one that starts last, and this is still an optimal solution. Like recursing on it to get the optimal answer will still give us the optimal solution for everything. Okay, so again, what we just proved is that by making the greedy choice of always taking the one that starts last, our answer is not going to get any worse, because here we started off with 3 as the optimal solution, but after swapping, it didn't get any worse. It's still 3. It didn't really get better, but it didn't get worse either. So it's still an optimal solution. Okay, so this means that there is still an optimal solution that has the one that starts the last, with the interval that starts the last. Okay, so that's the argument. So I'll quickly pause here for any questions. Okay, if it's okay, give me a thumbs up. I'll go through the counter examples in a bit. What about, okay, so there's a question. What about when it starts last, but it is shorter than the suboptimal last one? Okay, sorry. The problem here is not to find the shortest length, like shortest length of. The problem here is not to find the shortest length intervals. It's okay if you like spend the entire day. The problem here is to find the largest subset of mutually compatible activities, meaning you want the activity as many as possible. You want as many activities as possible. You can imagine like you want to take as many classes as possible. It doesn't matter that it's shorter or longer. right? So this last class can take like 10 hours, right? You don't really care. As long as you get that class, you are happy. Okay, so the problem is about maximizing. The problem is about maximizing how many activities you can do, right? Does this clarify? It's quantity, not the duration. That's right. Yes, it's the quantity. So we are maximizing over the quantity here. Thanks for clarifying with that. So, yep. So it's fine that you choose the one that starts last because it's about maximizing the quantity of activities. That's right. Okay. So I'll just quickly go through the rest. The option 2 does not work. Option 2 is the one that ends last, simply because if it ends last, right, we don't have a guarantee on when it starts. Because for example, right, it chooses ending last, chooses this guy, and then call it a day, right? It ignores everything else that conflict, right? But we know the optimal solution quantity wise is this two. Okay, quantity wise is this two, so it does not work. This is a simple counterexample. The shortest activity similarly can be shown, right? This is the shortest one, right? 3 to 5 is the shortest one. It conflicts with two others and then calls it a day, right? So it conflicts with two others and calls it a day. So this also does not work because clearly the optimal one is by taking two of these things. Okay, so option 2 and 3 do not work, and only option 1 as presented works for this problem. Okay, among the 3 options, only option 1 works. So okay, I'm almost done. Okay, this is just another exercise you can consider, right? Instead of starting last and ending last, I propose like, hey, what about we choose the one that starts the earliest, and what about if we choose the one that ends the earliest? Okay, so these are other possible greedy choices. It may work, it may not work, but I'll leave it to you to think about it. So if you want to try implementing, this code actually has a very similar problem, non-overlapping intervals. You can try for fun. Okay, again, take some time off, 3230, see if you can derive it again yourself. Think of the intuition again. Okay, and so to summarize, if you want to do greedy algorithms, you typically just choose one sub-problem chosen greedily, and then you prove that this greedy choice will still give you the best optimal solution by the cut and paste argument. Okay, so that concludes today's tutorial. I'll share the slides in the chat. And if you have any question, do feel free to check with me. I'll stay back for a while. Okay, so I run that meeting. Yep, so that's the slides, no problem. Yep, I hope this tutorial is slightly more relaxing compared to the previous ones. Okay, and if you don't have any questions, feel free to like call it a day. Yeah, thanks a lot for coming today. No problem. No problem. Any questions from the ones who are left, or archipelago? All right, see ya. Or the other two? Maybe I'll wait till like 11:58 in case, you know. Okay, I guess I suppose you are good. If you don't, if you're not, then do let me know over chat or something like that. All right, so I'll stop the recording. Thanks a lot for watching this video if you are watching it over video.